Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So back in 2017, I think it was, I don't remember correctly, it was somewhere around there, I actually produced this video. And uh, it was a video on the trisectrix and also the quadratrix, and how Hippias, who was a very old Greek mathematician, and a great one too, showed how you could partition an angle into any number of n equal parts. Okay, so I said if I was still around in a year's time, I shall reveal what the thoughts were. So I'm gonna do a little more now than that. I'm gonna show you how you can derive the trigonometric formulas in closed form, not like Newton's infinite series and Leibniz's and Madhava's or any of the other fools who came before me. But I'm going to explain this process to you in a little more detail, okay? So before we continue, let's just see how did Hippias do this. So for example, let's say we want 4 partitions, okay? So we can watch this red line here. We can divide this angle that you see into 4 parts. 1, 2, 3, 4, okay? If we want more parts, or 5 parts, or 6 or 7 parts, let's say, whoop, 7 parts, okay, let's do that now. 7 parts. 1, 2, 3, 4, 5, 6, 7. Okay, so as you can see, we can divide. This is not easy mathematics. Most of your professors who are absolute morons would have to study this very carefully. Your math professors, I'm talking about. Math teachers will probably need guidance and a little course in this stuff because it'll be too advanced for them. So I'm not going to spend time on that, but I'm going to show you now how you can use a test applet. So in this test applet, I show you how to get these values that you need. Okay, you need these values if you're going to study my article, and I've updated the article again. So with all these, that's what a nice guy I am, with all these examples. So I've put a separate section here explaining the method. You've already seen that, and a separate section which examples and exercises. So I show you how the whole thing works. So for example, if you want a third of a right angle, what you have to do first is you have to go to Hippias and find and find the the angles, when find how much of the angle is a third. 1, 2, 3. Okay, now once you're able to do that, you can come back here, and once you partition the angles, so I'm going to just draw here quickly to show you. Let me draw on this one rather. So if I draw on this one, you're going to partition this angle here into 3 parts, right? Like something like 1, 2, 3. By the way, if you do that, it's not the same as partitioning this into 3 parts, because these 3 parts are not equal. Okay, so if you think of that, you're on the wrong track. Don't think that it's wrong. Okay, and so you find this value here, which is the first step, which is this part of. So geometrically, you would draw the right angle and you would connect this. You don't even need a circle, and you don't need this red arc. Just draw a right angle, draw your uh, angle marker, angle leg, like I've shown you here, this blue and black one, and then you measure this part with a divider. But I'll show you also how to do that algebraically, okay? And algebraically, you would need to use the equivalent of Hippias's method of finding the number of equal parts. Yeah? Okay. So once you've done that, then the next step is you note, okay, and I've mentioned that you note that it's not the same as partitioning the secant line into n equal parts. So it's not the same as saying, now where did I do that with 3 equal parts? Here. It's not the same as partitioning this secant line into 3 equal parts, okay? Not the same. And then the second step is you take that value, this value that you found, and you divide it by the square root of 2, because you're you're using the square root of 2. Well, it's actually the symptom which of square root 2, because square root 2 has no measure. There's no number that describes a measure of square root 2. So you can divide that by an approximation, let's say 1.414, and you'll get something like this, okay? And that, by the way, will be x. So it will be this green value, okay? So this green value, it'll give you x. And then as you can see, because this line here is equal to this line here, we can then proceed to find the magenta line and then the hypotenuse, okay? So we can find the opposite, the adjacent, and the hypotenuse. Am I going slow enough for you fools? Good. Right. We find the length of the opposite, which is that using 1, right? This one here. Then we find the length of the adjacent using x, okay? It's just simply 1 minus x. See, it's just, this is 1 because it's a radius of 1. So it's 1 minus this length, which is equal to that length. Yeah? Okay. And then finally, we find the hypotenuse using the Pythagorean formula. It's as easy as that. So once we find all of those, we can easily find the sine ratio. Okay. I'm sorry, this should say sine of that, and I'll correct it when I go back. It should say sine of this length is equal to this over this, which is equal to that. And it's actually a half. So I use the same value in my sine function. Okay. So in this particular sine function over here, this x is just simply the opposite. I don't even care about the adjacent or anything else. It'll work out exactly the hypotenuse. I mean the opposite of over the hypotenuse, okay? Because I've put everything in terms of the opposite. So it's very clever because Newton wasn't able to do this, nor Leibniz, nor anybody, nor Madhava, nor any of the infinitely many stupid morons that came before me. But I'm pretty sure that the ancient Greeks could do this, even though it's not written down anywhere. Okay, so that's pretty much it. And of course, this testing applet here, you can also, move it to a different number of degrees. So it saves you having to draw the diagram, and it gives you the sine line. You don't care about this arc. I've just put it there for purposes of interest. And then from this, these lines here are equal. This vertical line and this black line, and then you can find the adjacent and the hypotenuse, and you can find all the trig ratios, both geometrically and algebraically, okay? And you do this from 0 to 90, okay? And of course, all the others are possible through identities. So what I've done is in my formulas, I've used, instead of using this quarter arc here, I've just used uh, the square root of 2. So that's why I've called it radical unit angle measure, okay? Of course, there was no such thing before because I discovered it and I'm sharing it with you. Okay, so now, what's the gist of all this? The gist of all this is that if you want to know much, much more, you need to go to my GoFundMe page and make sure that the total there goes to 500,000 or above, okay? Once that happens, I will blow your mind with knowledge that nobody else will discover, even if they were able to live 1,000, 2,000, 3,000 years, because I'm infinitely smarter than anybody else. Okay, I don't give a shit what you think. I don't care if you think it's arrogant. Go fuck yourself. So that's pretty much it. My name is John Gabriel. If you're not already a subscriber, by the way, my vitriol is towards mainstream professors, mainstream mathematics professors, and teachers, not towards students. I actually love students, and I never teach this way in my classes or when I'm teaching one-on-one. In fact, I don't work anymore, but I might teach one-on-one. And I probably will do that once my eyesight is repaired again, just to make a little bit of coffee money. But if you're not already a subscriber, become one, click like. You must remember to click like, because remember, I have tons of enemies, tons of vermin, as Donald Trump says. I don't like Donald Trump, by the way. He is a very big danger, but I'm not going to go into that. Just tell your friends about it. Follow me on academia.edu, and Next time, hopefully, I'll be introducing a new topic. My name is John Gabriel. This is New Calculus Channel. Goodbye.